Good morning. Welcome everyone to the third part of our odor control webinar series. My name is Methalyn Murphy and I'm going to talk today about pH shift products to control hydrogen sulfide odors in wastewater. This is the third webinar in our odor control series. The presentation is going to go over pH and how it relates to hydrogen sulfide, and then how we use that relationship to control hydrogen sulfide odors. I'm going to go over some different pH shift chemistries used for odor control, their pros and cons, and applications where pH shift products would be the best fit. Go over some of the Alkagen options that Evoqua offers, which is our calcium hydroxide slurry, the equipment that we use to feed the product. And then lastly, I'm going to go over a couple of case studies. The first one, a pilot study performed by the City of LA. That compared the ThioGuard or magnesium hydroxide slurry versus our Alkagen product, which is the calcium hydroxide slurry. And the second case study will be an example of the bauxite AE process in practice. The idea behind pH shift products to control hydrogen sulfide odors is to introduce chemical into the wastewater to raise the pH enough so that sulfides are then trapped in solution and prevent the release of hydrogen sulfide gas into atmosphere. Sulfide in solution exists in one of three forms, either as a dissolved hydrogen sulfide gas, the bisulfide ion, or the sulfide ion. The dissolved hydrogen sulfide is the most volatile of the three ionic forms, and with turbulence is likely to get released into the air and cause odors. In addition, the lower the pH is, the more hydrogen ions are present, and they repel each other, really promoting the release of hydrogen sulfide gas into the air. So the pH of the wastewater is really what determines the prevailing form of sulfide that we're going to see in solution. So increasing the pH, the dissolved hydrogen sulfide shifts from one of the non-volatile ionic forms, which is the basic goal for pH shift products. This graph right here is illustrating how the ionic form of sulfide shifts with the pH. The lower the pH, the more likely sulfide is in its most volatile dissolved hydrogen sulfide form. And as pH increases, the sulfide ion then shifts into the bisulfide ion or sulfide ionic form. And those are the non-volatile forms of sulfide. So as you can see, at a pH between 8 and 9, nearly all the dissolved hydrogen sulfide ions have shifted into the non-volatile states. And so raising the pH above an 8.5 to 9 is really the target when using pH shift technology. This graph measures real-time hydrogen sulfide gas at the control point of an Alkagen application, and it really illustrates how quickly that sulfide form shifts once pH chemistry is introduced. Before the system was started up, we were averaging around 50 ppm, and almost immediately on startup, the gas drops significantly and starts averaging less than 10 ppm. You can really see the point at which the pH shifts above the 8.59 range, and that sulfide shifts into its non-volatile form. Some of the common pH shift products for odor control include sodium hydroxide or caustic, which is highly soluble but is very corrosive and considered a hazardous product. And for that reason, caustic is not typically used for continuous long-running odor control. A more common option we see is magnesium hydroxide, which is a non-hazardous product and is self-buffering, meaning no matter how much more magnesium hydroxide you add, the pH theoretically would not get much higher than an 8.5, which is good in that you can't raise the pH up too high, but also it makes it difficult to control and monitor for an overfeed situation. Overfeeding can contribute to some accumulation of solids in the wet well or the line itself. Also, feeding magnesium hydroxide introduces magnesium into the wastewater, which can be a problem downstream at treatment plants where struvite can form. Struvite is a crystalline deposit, and it contains magnesium, ammonia, and phosphate. Ammonia and phosphate are very abundant in wastewater digesters, and so by introducing the magnesium, it can make the potential for the formation of struvite possible. And this crystalline deposit can really cause major damage to the plant by clogging pipes or damaging equipment. So it's just something that something to be aware of and to be avoided. And then there's calcium hydroxide, which is the pH shift product that Evoqua offers. Our trade name is Alkagen. It is not self-buffering, so it has a wide pH range. The feed rate can be controlled to a specific pH or pH range, and we can assure that we're not overfeeding. There's a couple of different Alkagen blends that we offer. The Alkagen AQ is a 25% calcium hydroxide slurry with an aquit adder. The aquit is a proprietary chemical that limits the formation of sulfide in the slime layer of a force main. And then Alkagen is our straight 45% calcium hydroxide slurry that contains about 5 pounds of calcium hydroxide per gallon. Some of the benefits for pH shift technology include that its ability to quickly dissolve, which means that not only can we use it for downstream odor control at force main discharges, but we can often use a pH shift product for point source odor control. It's also, our particular Alkagen product is easy to control, as I mentioned. We can really target a specific pH and keep it within a certain range of pH. Introducing a pH shift chemical can also reduce fats, oils, and grease in the wet wells. So if you're seeing issues with matting, an Alkagen could help resolve those issues. And also adding some sort of pH shift chemical like Alkagen can provide additional alkalinity into the wastewater, and that can be beneficial for a lot of the treatment plant processes downstream. Some of the recommended applications for pH shift chemistry include headworks odor control. We've fed Alkagen at an incoming manhole to a wastewater treatment plant or an incoming pump station, and using Alkagen in that way, we're able to shift the pH of the entire flow coming into the plant so that by the time it hits the headworks, those sulfides are being suppressed into solution. We've also used Alkagen in the collection system for local wet well odor control. We'll feed Alkagen at an incoming manhole and be able to feed at the wet well itself, to control odors at the wet well itself, and then also downstream at the force main discharge. Alkagen can also be used in conjunction with bioxide in the patented bioxide AE process. So in larger applications where there are multiple bioxide sites throughout the collection system being repumped from one station to another, the customer can potentially save money by increasing the pH upstream of a bioxide site, using bioxide in its removal mechanism, which is 2 times more efficient than bioxide in its prevention mechanism, and just save the customer in overall chemical spend. Bioxide in both its prevention and removal mechanism was reviewed in the second webinar of the series, so if you're interested in learning more about that, I suggest checking that out. We've also used Alkagen in gravity interceptors. We've used Alkagen in instances where they're doing work on gravity lines. So if the city was going to do some repair work on concrete or have to expose a gravity interceptor to the atmosphere, we've been able to feed Alkagen right at their work site and control odors where they have the water open to atmosphere. pH shift chemistry can also be very cost effective for applications with high sulfide levels because we're not treating for pounds of sulfide, we're really just trying to shift the pH of the wastewater flow. So depending on the flow and how much sulfides are present in the system, Alkagen can be a very cost-effective solution. And as I mentioned, for applications with fog issues or matting issues, a pH shift chemistry can help dissolve those issues. There are situations where pH shift might not be the best fit, and that would include force mains that are greater than 12 hours in retention time. It's hard to feed enough chemical to really keep the pH elevated for that long of a force main. And over time, wastewater just turns more acidic, so it brings that pH back down, and any benefit you saw from adding a pH shift chemistry is then lost. Systems with significant industrial flows, a lot of times industrial flows come out with a pH less than what is typical in wastewater and can cause higher feed rates for pH of chemistry. So we tend to avoid using Alkagen in industrial applications. Systems or applications where you have additional flows joining the treated flow after we've fed the Alkagen. You really only get odor control treatment when the pH is elevated. So if you have treated flow and other flow is joining in downstream, that pH is going to drop, and then you lose the benefit of suppressing the sulfides in solution. If an application has dissolved sulfide goals, specific dissolved sulfide goals, Alkagen or a pH shift chemistry really wouldn't be a good fit because you're not getting rid of any sulfides, you're really just suppressing the sulfides into solution. And then if the control point happens to have a lot of turbulence, even just a small amount of dissolved hydrogen sulfide in liquid form can get released into air with a significant amount of turbulence. The feed rate of a pH shift chemical is really determined by the volume of flow. For our 25% calcium hydroxide slurry blend or Alkagen AQ, the rule of thumb is about 150 gallons of Alkagen AQ per million gallons of flow. And for our 45% calcium hydroxide slurry or Alkagen, we estimate about 75 gallons of chemical per million gallons of flow. For any specific application, we try to do a titration. So we take a diluted sample of the Alkagen that we're going to use and then a sample of the wastewater and titrate to determine how much chemical is required to get the pH between an 8.5 and 9. And that way we can really accurately determine how much chemical is required for that specific system. This is a picture of what our Alkagen systems look like. We've got a tank, a submersible mixer in the tank to keep the slurry mixed. We have a water flush system that flushes water back to the tank and then out through the discharge line. Every system comes with a VersaDose control panel, which allows for advanced dosing capabilities. We can program in a 24-hour dose curve, so each hour of the day will have a specific dose rate. There's also the ability to include a flow signal, so we can flow pace the chemical based on the varying flows throughout the day. And each tank also has a submersible mixer that keeps the slurry mixed inside. The first case study I'm going to go over is from the city of LA. They conducted a two-part test that compared the performance of Alkagen with magnesium hydroxide. The first part of the test treated biosolids coming from the LA Glendale water reclamation plant, and the second part of the test went over, treated the Tillman water reclamation plant. Both of those plants are sending biosolids down to the Hyperion treatment plant for those biosolids to get processed. The first part of the test had the two vendors feed chemical at 3 different feed rates, 500, 600, and 700 gallons per day. And we were treating 60 million gallons a day of flow from the LA Glendale plant. The gas was monitored at 2 control points downstream. The first one 3.2 miles downstream and the second one at 5 miles downstream. Alkagen at all 3 feed rates, the average sulfides was around 2 ppm at the first control point, where mag hydroxide ranged from 4 to 19 ppm. And further down the line, Alkagen still performed well against mag hydroxide, averaging between 1 to 4 ppm, while mag hydroxide measured between 8 and 12 ppm. So on average, Alkagen performed 2 to 9 times better than the mag hydroxide for the first portion of the test. For the second part of the pilot study, Alkagen and mag hydroxide were tested in comparison along a much larger and longer interceptor. The Tillman plant sends approximately 80 to 90 million gallons of flow down to the Hyperion plant. And in this part of the test, the vendors were allowed to optimize for their best gas performance. And Alkagen landed around 1,700 gallons per day. And the thiogod product was fed between 1,800 and 1,860 gallons per day. And both were resulting in similar sulfide results. So Alkagen was able to get similar sulfide results to the Thiogard at a 9% lower dose rate. The LA study proved that Alkagen performed favorably against mag hydroxide and could achieve equivalent to lower hydrogen sulfide levels at lower dose rates. And while we don't typically suggest using Alkagen for very long detention times, the study proved that Alkagen could control hydrogen sulfide over long distances in this particular application from a single chemical addition point. And the study proved that Alkagen was a cost-effective product to control hydrogen sulfide in the collection system. The second case study I'm going to go over is showing the bauxite AE process in practice. This particular municipality was feeding almost 500 gallons a day of bauxite to control odors at their Bombay lift station and IPS lift station. And that was the best they could do within their budget, but they weren't really happy with the sulfide results at Bombay or downstream at IPS. So we suggested feeding Alkagen at the preceding lift stations at Sweetwater and London Bridge to elevate the pH, and then feed bauxite at the Bombay lift station to remove the sulfides altogether, in the hopes of giving them a better sulfide control with less chemical use overall. And so we were able to give them about a 28% cost savings. Their total chemical use per day with the bauxite only program was 500 gallons a day. And with the bauxite AE program, they were only using a total of 325 gallons of combined chemical a day. And this achieved much better sulfide results at the Bombay lift station, as you can see in this graph. The bauxite AE process provided significant cost savings while providing better sulfide control. At the Bombay lift station, the average sulfides were reduced by 82%, and at the IPS lift station, they were able to control their sulfides within their 100 to 150 ppm goal. And this is all while reducing their average daily spend by 28%. So that concludes the pH shift technology portion of the presentation. Next week will be part 4 of our series, and that will focus on air scrubbers. Justin Stewart, another applications engineer, will discuss how air scrubbers can be used to control odors at the source or provide supplemental odor treatment for chemical-based programs. Feel free to drop me or Calvin Horst, our product manager, an email to get information on something that you need. Thank you for your attention.
So starting with the first question, Matthew, we have, will a pH shift product create higher sulfide loadings downstream, for instance, at the treatment plant? And if yes, would you recommend complementing pH shift treatment with other sulfide mitigation technologies?
Yes, so as I mentioned, pH shift chemistry really doesn't get rid of any sulfides, it just keeps the sulfides in solution. So if you're only using Alkagen, you're really just keeping the sulfides in solution, you're not getting rid of it. So if you are looking to get rid of sulfides, we recommend using something like bioxide or calcium nitrate or another chemistry that will actually remove the sulfides from the system.
Great, thank you. Another question we have, is it possible to use ferric hydroxide slurry for pH shift? And I'm happy to answer that one, or you can take it as well. Happy to. So I know that there are definitely studies out there that have shown that ferric hydroxide has been effective for wastewater odor control. I'm specifically thinking of one that was done 7 or 8 years ago, where they used it to reduce odors in a sludge treatment process, and it was effective, I believe. They got to 90% or so reduction in odors in that particular application. We have a question on common stock solution concentrations for sodium hydroxide, mag hydroxide, and Alkagen. Do you want to cover that one, Methy? Would you like me to?
You can do that.
Okay, so we talked about our Alkagen solutions being the Alkagen solution, which is a 45% solution, and Alkagen AQ, which is the 25% Alkagen solution with anthraquinone added. Common concentrations for magnesium hydroxide that we see used in odor control applications, typically 50 to 60% solids. And sodium hydroxide, really, you can get in a variety of strengths, but commonly available would be, in the range of 25 to 50% and up from there. For cold weather applications, are there any special storage requirements?
Yes, so for cold weather applications, we would have to use a heat trace tank and heat trace lines because calcium hydroxide is susceptible to thickening with colder temperatures.
Great, thank you. Matthew, on the second case study, was the system flow, what was the flow rate that was treated in that particular application?
So the flows were relatively low. At the Sweetwater site, the flow is around 1 mgd, so we were only feeding about 75 gallons of Alkagen. And then the second lift station that was going into that Bombay lift station was around 0.75 mgd, so we were feeding 50 gallons a day of Alkagen there. And so that helped really with the cost effectiveness of it. It wasn't high flows, so we didn't have to treat with a significant amount of Alkagen to elevate that pH and get the benefit of the bauxite at the Bombay lift station. So yeah, the flows were fairly low.
Great, thank you. We have a question about special considerations for combined sewers. Do you want to take that one, or would you like me to answer it?
Sure, you can take that one.
Okay, so with the application of pH shift products, really we're treating the total flow. So that in most cases would be the total flow of the wastewater to raise the pH at a particular point. In combined sewer applications, of course, we have to worry about runoff and rain events that contribute to that. So it may make it a little more difficult to control. And with calcium hydroxide as a pH shift product, we're adding ions into the wastewater, and we have to consider the hardness of the water that we're treating, the pH targets that we're trying to achieve to control odors to ensure that we don't end up with scaling. So we would consider the Langmuir saturation index in that case and make a decision on the possibility of scaling there and weigh that when we're selecting an odor control solution.